Hello APCal class, we're continuing on with the 2.4 notes and moving on to example 7. So before that, we're going to take a look at the trig functions that would involve the chain rule. So we looked at these before: derivative of sine, cosine, derivative of tangent, secant squared, derivative of secant, secant tangent, and then their cofunctions over here. So the one thing that we're going to follow up with here is if it's, so they're putting a u in here, like derivative of sine of u. And it's still going to be cosine of whatever that u is, but then we have to multiply by the derivative of u. So here, rather than just having an x, maybe it's a 2x or an x squared. So when we do the derivative of that, we would have cosine of, let's say, 2x, but then times the derivative of 2x, which would be times 2. So we have one extra step there. So like right here, to find dy dx of sine of 2x, we know that the derivative of sine is cosine, so we're going to say cosine of 2x, but then we have to multiply, so just like it says right here, we have to multiply by u prime. So if u is 2x, multiply by the derivative of 2x, which is times 2. So to make that look a little better, we're going to put the 2 in front, 2 cosine 2x. So that's how we apply the chain rule to a trig function. Okay, in a similar way here, the derivative of cosine we know is negative sine, but because we have an expression here, 3x minus 1, then we'll multiply by the derivative of 3x minus 1. So dy dx is going to equal negative sine, and then we keep 3x minus 1, but then we multiply by the derivative of that, which would be times 3. And so when we do that, it kind of gets a little ugly, put it at the end, but times 3, I'm going to multiply that 3 here, so I'll have a negative 3 as my coefficient. So dy dx equals negative 3 sine, and then 3x minus 1. Okay? That way we don't have to have all this grouping symbol stuff in here, but put that as your coefficient. All right? And then for part C, secant, so the derivative of secant is secant tangent. So we'll do that, and we'll keep the 4x with the secant 4x tangent 4x, and then times the derivative of 4x right there. So if you're thinking ahead, so that I don't always have to kind of pull that to the front, I'm going to have a 4 as my coefficient, right? So dy dx is I'm going to put that 4 in front, and then I'll have secant 4x and tangent 4x. Got to squeeze together there, but that should be our derivative there. So hopefully that one makes sense. So next up, we're going to look at, just give me 1 second here to clear something. Okay. All right. So here we have, it says trigonometric functions that require repeated use of the chain rule. So there's like a chain within a chain. So these ones are, they're fun. I'll just say that they're fun. Okay, so it's actually not too bad. It's we just have to recognize how many chains are going to be involved here. So when we have an exponent here, I always, before I do a derivative, I think it's helpful to rewrite that as sine 3x, and then technically, so that we recognize it as the first thing we have to do as our outer function is the power rule, where we have a 4th power. So we're going to do that first, okay? So when we apply this power rule, dy dx, so we're going to have 4, and then inside here we've got sine 3x, now to the 3rd power. So now I've still got 2 more functions involved here. I've got the sine of something, and then the something that's not just x, it's 3x. So now the next thing I'm going to do is the derivative of sine 3x, so that involves a chain rule as well. So that's going to be, the derivative of sine 3x is going to be cosine 3x, and then I also have to again multiply by that 3, right? So the 3 I would just multiply by this coefficient of 4, and so we're going to have 12 in front. Okay, so dy, so I'm going to have 12 here. I'm going to have sine 3x cubed, and you know, if you want to at this point, you could change it back to make it look a little neater. You could just put it back as that little exponent in between. So we could put our cube back at that point, and then we would have our 3x and then cosine 3x. It's going to look more like that. Okay. So in a similar way, I would say this one is fairly similar because we haven't technically an exponent over the whole thing because that's a square root, which really means, that means a 1/2 power, right? So if I rewrite this, I'm going to have secant of x over 2 all to the 1/2 power. And so when I do derivative there, that's going to be dy dx equals 1/2, and then this would be secant x over 2, and then that's going to be to the negative 1/2 power. So there I've done the power rule, and then I want to do times the derivative of secant 1/2 x, or x over 2. And so the derivative of secant, we know that is secant tangent, so that's going to be secant x over 2 tangent x over 2, and then times the derivative of x over 2, which is just times 1/2 again, right? So times 1/2, so the derivative of the x over 2, which is just 1 over 2, right? And so in the end, as I kind of clean this up a little bit, I want to look for those negative exponents and say whatever is to a negative power is going to drop down into the denominator. And I've got a 1/2 and another 1/2, which is a 1/4. And so you could leave the 1/4 out front if you want to. I usually take that and put it in the denominator as well. So I'd have like a 4 down here because I'm multiplying by 1/4. And I can just make one big fraction here. And so then I've got secant of x over 2 to the 1/2 power, which is going to go back to a square root of secant of x over 2 like that. And then what's left in the numerator? I've got this expression here. So, and remember, this is the 1/2 times 1/2. That's where I got my 1/4 technically, right? So multiplying those, so that's why I've got the 4 in the bottom. And so on the top, I've just got secant x over 2 and tangent x over 2. And then that should be good. So hopefully that makes sense. The 1/2 times 1/2 is 1/4, and technically that's what I have here, right? 1/4. And then this negative exponent dropped it down to the denominator, so I have a square root of secant of x over 2 there, and this expression here is left up top. Okay, so there's my derivative of that expression. Okay, next one. I left this one worked out just to maybe save us a little bit of time, but so here again, so it's similar to these others. It's cotangent this time. So I've got cotangent of 3x over 2 to the 2/3 power, and so applying the power rule first, 2/3 gets multiplied down. Take 1 away from 2/3, and that's negative 1/3. So I have cotangent 3x over 2 to the negative 1/3, and then I have to do the derivative of cotangent of something, and the derivative of cotangent of u is negative cosecant squared of u, and so negative cosecant squared of the 3x over 2 times the derivative of the 3x over 2, because I have to do my chain rule there again, similar to what I had to do on all of these previous examples, right? And so that's basically, that's it, that's the derivative, but we'll clean it up by taking this piece down to the denominator and making it a positive exponent. It started with rational exponents, so I'm not going to change that back into a radical like I did here. I'll probably just leave it as a 1/3 power. But then the rest of this is going to stay up top, so this is going to stay in the numerator. And actually what happens in this one, conveniently, is that the 2/3 that got multiplied down in front, and then this 3/2 that was part of my chain rule, because the derivative of 3x over 2, when I multiply those, they kind of cancel each other out. So that kind of simplifies nicely, and I'm just left with this expression. Okay. All right, so then the last couple examples are going to involve the natural log and then the exponential base a instead of just base e. It could be like a 2 to the x or something like that we're going to do the derivative of. And so the derivative of the natural log, ln of x, is a fairly simple one. Basically, it's just 1 over x. Okay, so that's all that one is. And if it's ln of u, something other than just x, like if it was x squared or something like that, it's going to be 1 over whatever that u is, 1 over x squared, let's say, and then times the derivative of that. So it'd be like times 2x then. right? So it's, and another way to write that is u prime over u, so the derivative of u over u. But so you put it in the denominator, and then you use your chain rule to do the derivative of u multiplied afterwards, okay? This other box is just a review of some log properties that hopefully you remember some of them. But the log of 1 is always equal to 0, because if you recall, like a log, really what that means, so ln of anything, really, okay, so let's say it's ln of 1, right, equals, and then you're saying, what does that equal? It equals something, right? Well, ln, it's a base e, right? So what we're saying is e to what power would equal 1? Well, regardless of the base, whether it's a base e or a base 2 or a base 100, whatever, anything to the 0 power, so you're asking yourself, e to what power equals 1? And so the answer to that is 0. Anything to the 0 power is 1. So the log base anything of 1 is always 0, okay? Some other properties, if you're taking a log of a product, you can, because logs are basically an exponent, you can write them in exponential form. They have similar properties to exponents. So ln of a times b would be like ln of a plus ln of b. Okay, so just like when you multiply, x squared times x cubed, you add the exponents together. It's kind of like you add, if you're multiplying here, you can add those logs together. So you can expand a product by taking the log of each and adding them, okay? And similarly with, if you have log base of a to the n, you can multiply that exponent down, n times ln of a, so that can get multiplied down. Just like it's similar to the power rule. You don't have to subtract anything from that, but you can just multiply it down. But it's kind of like with exponential, properties. If you're multiplying with, or if you would have a power to a power, you multiply those powers together. And then with, if you have a log of a quotient, you can take the difference of those logs separately like this, okay? So sometimes these are helpful to simplify. If you have a complicated expression, you can use some of these properties to simplify before you do the derivative, okay? I think that's what we do on part E here. Okay, so for part A, pretty simple one here. So like we said, if we have an ln of something, it's going to be 1 over that something times the derivative of that something, right? And so it just ends up being 1 over x. And the other way, it's u prime over u, right? So u prime would be 2, so I'd have 2 over 2x, and that's what I have here. Simplifies down to 1 over x. Okay. Here, again, we don't really need to simplify it at all. I think we can just use our derivative rule for natural log, which is 1 over whatever you're taking the log of, and then times the derivative of that log, which would be 2 times 2x, like that. And so that's why they say u prime over u, because basically you can just put that part in the numerator. So I could just say that, I can just say that it's 2x over x squared plus 1, okay? Referring back to basically this u prime over u, which is the same as 1 over u times derivative of u with respect to x. U prime over u is an easy way to remember that. Okay, and that's what we get right there. Here, again, we have an ln, but it's a product rule, so we have to recognize it's x times ln of sine of x. So this is a product right in here. So think, what's big picture here? I have a product to start. Within that product, I'm going to have to apply a sine or an ln property of doing derivatives in there, because that product rule goes derivative of the first, so that's just going to be 1, and then times the second, which is ln sine of x, right? And then plus the first times the derivative of the second. Now the derivative of the second is going to be 1 over sine x, and then times derivative of x. So there's really no chain rule necessary there, because it's times derivative of just the x, and that's just 1. So product rule, remember, first times the derivative of the first times the second plus the first times the derivative of the second. So first times the derivative of the second is going to be 1 over sine of x for that one. Okay, so then we can simplify that one just a little bit more, which is going to give us, oh, hold on here one time. So I did, derivative of the first times the second ln of sine plus the first times the derivative of the second. Okay, so actually, I forgot to, it's not, when I do my chain rule here, I do have to multiply by, I messed it up, derivative of sine, so I have to multiply by cosine on this one, right? Because my ln of u is actually sine of x, not just x, okay? So it's going to be 1 over sine of x times the derivative of sine of x, which is cosine of x. Okay, so I should have a cosine of x there. So when I simplify this, I'll have ln sine x plus, and then here, cosine of x over sine of x, which I could call cotangent of x. So I could call it x times cotangent of x, because cosine over sine would be my cotangent there, okay? So I can leave that one like that. And then for part D, dy dx, so for this one I would just bring that 3, I'm going to use my power rule first, 3 ln of x, and then that's going to be all squared like that. And then I would go times the derivative of ln of x, which would be times 1 over x. And so I'm going to have 3 ln of x, and then this would be squared. And then I would have all over x like this. Okay. All right, so this last one I kind of left worked out so that we could talk about it a little more quickly too. We apply a lot of properties of logs before I do any derivatives here. You can just see I'm just saying y equals, and then I'm going to use some of these properties. So in the numerator, like I have a product of some things, so I can separate that with addition, right? ln of x plus ln of the x squared plus 1 squared. And then since I'm subtracting next, I can dividing, I can subtract that, right? So with these log properties here, these aren't derivatives, these are just log properties. If I have a product, I can add the two pieces. If I have a quotient, I can subtract those. So that's what I'm going to do, because that'll make doing the derivative much easier than trying to do a product rule and a quotient rule and all that stuff. So if you can apply some log properties first, that's helpful. Okay, so I've done that here. And then next up, because I do have a power right here, I can multiply that power down, and that's not a derivative, that's just a property of logarithm. So if I have a log of something to a power, that power can get multiplied as a coefficient there. Similarly here, because we had a square root, I can take that one and multiply it down as a coefficient. Now this is fully expanded, and now it's going to be much easier to do the derivative. So now when I do my dy dx, ln of x is just 1 over x, okay? And then this next piece, and then this ln is going to be 1 over x squared plus 1 times the derivative of the x squared plus 1, which is times 2x there. And then in the last piece, I can do the ln of this, which is 1 over 2x cubed minus 1 times the derivative, 2x cubed minus 1, which is 6x squared. And so cleaning all of that up, this first piece doesn't change. The second piece, 2x times 2 is 4x, that'll go in the numerator, and my denominator will stay x squared plus 1. And here, 6x squared times half is going to be 3x squared, so I'll have that in the numerator, and the denominator 2x cubed minus 1. Okay, so if you can apply those properties of logs before you do the derivative, expand it out the best that you can, then that makes the derivative piece much easier. Okay, the last couple formulas these are much lesser used, but I'll go through them real quick. It's going to be a derivative of a base, like a to a power, and then a derivative of log base a. Okay, and then these are just the chain rule versions of them. Okay, so if you recall, there was a change of base formula that you probably talked about in your algebra or college algebra, which, like, if you have a log base 2 of something, like if it was log base 2 of 27 or something like that, you could take log of 27 divided by log of 2. So in a similar way, if I have log base 2 of x, I could take ln of x over ln of 2. And I can do any base here, but ln is helpful to use here. And so this one kind of helps explain how we do the derivative here. So if we have log base a of x instead of just ln of x, we can do, we can think of it like this. The derivative of ln of x is 1 over x, but then this coefficient of 1 over ln of 2, that stays there in the denominator. So the ln of whatever that a was ends up getting divided in the denominator there. Okay, derivative of a to the x, just like derivative of e to the x is e to the x, derivative of a to the x is a to the x, but then you also have to multiply by ln of a. Okay, so these ones I did leave kind of worked out so we could talk through these quickly. So derivative of 2 to the x, it's going to be 2 to the x times ln of 2. All right, so you got to remember to multiply by ln of 2 there. if we have derivative of 2 to the 3x, okay, so that would be an example here where we have something else like a to the u. It's still going to be 2 to the 3x times ln of 2, and then times the derivative of the 3x, which is 3. Okay, so it's going to be, we really can't multiply anything out here. Like, you can't take the 3 times, because this is 2 to the 3x, so you just have basically 3 separate products there, things being multiplied. Okay, and then the last one here, log base 10 of cosine of x. All right, so we're going to do, like, basically we're going to do that ln of cosine of x divided by ln of 10. That's another way that we could rewrite this. I explained it this way just to, if we did like applied a change of base kind of formula to it in a way, because I'm not doing the derivative yet. But if you have, like a log base 10 of cosine of x, I could think of that as, I can change it to any base I want. If I do ln of cosine of x divided by ln of 10. Now, ln of 10 that's just a constant, so really that you can kind of pull that off to the side. And now I can do the derivative of this ln of cosine of x. So the 1 over ln of 10 just kind of stays there. Derivative of ln of cosine of x is 1 over cosine of x times the derivative of cosine of x, which is negative sine of x. And so I could rewrite this expression. This would basically be its derivative, but sine over cosine is tangent, so I could write that as tangent instead of sine over cosine, and it's negative dividing by the ln of 10 there. Okay, something like this is not something you're probably going to do very often, but you might have to go back and review the rules on that, but I think it is helpful to rewrite it as a change of base kind of a thing, and then because the derivatives of the ln's are probably easier than the other bases for logs. But that's it. That's the end of 2.4.